Hi everyone, today we're gonna explain how to design a simpler supported one-way slab as per Eurocode 2. Okay, what you can see here is a simpler supported slab. It is resting on a brick wall and it has an effective span of 4 meters. And why I'm saying this is a simpler supported slab is because it is resting on a brick wall. Well, it can be a block wall or it can be any kind of load-bearing wall. But in this example, we are having a brick wall. That really doesn't matter what kind of material you are using here. Even if it was like a beam, it's still a simpler supported slab. And if you're gonna view it in this way, if you're gonna have a plan view, you'll see that the notation for the simpler supported condition is this one here. This is used for a simpler supported slab, okay? And since it is only supported by two or just on 2 sides, not on all the 4 sides, then it's immediately or instantly considered to be a one-way slab, irrespective what kind of dimension you have in the either transverse or longitudinal direction. That immediately makes it a one-way slab. Now we have this effective span of 4 meters. We have this slab, it is a one-way slab, and if you divide it by 2, this portion, this support here, or the brick wall, load-bearing brick wall, would take care of this portion of the slab. Any load lands on this portion will be taken by this support. The same thing happens here. So we want to take the effective span here, and we want to take 1 meter strip. This is our B. So the B is something fixed. It is 1000 millimeter. It is always this number. That makes the design easier. The simplest one to design is the slab always, because the stress is very low compared to the beams, which are usually highly stressed members. So what you want to find usually in the slab is the depth. You want only to verify the depth of the slab. So if you look at this example, we have the live load here. It is given as 3.5 kilonewton per meter square. This is a floor load, and you can always refer to the Eurocode for the live load categories. We are also given the dead load, which is 1 kilonewton per meter square. The dead load can be like floor finishes, stuff like that. The grade of concrete is C30, and we are given as well the grade of the steel, 500 Newton per millimeter square. That's the yield strength. There's something important as well. It's the wall thickness. We will need this for the shear force calculation later on. So we're starting with this formula here. In order to find the D, remember, for the slab design, you only need to verify the D, the depth, the effective depth. That's the only thing that you have to work out and then verify it. So in order to work out the D, you're gonna initially need something called the rho. The rho here is the percentage of steel in a cross section of a slab, okay, or a beam. Usually when you are dealing with slabs, the stress is quite low, so that makes the percentage of reinforcement quite low as well. So it is 0.3 up to 0.5%. That's the rho. That's the percentage of steel in a cross section. Unlike when you're dealing with beams, it is quite highly stressed members, so that makes the steel quite crowded in that cross section. So it is between the range of 1 up to 1.5%. That's for the steel. That's for the beam. Remember always, the minimum rebar set by the Eurocode 2 is 0.13%. That's the minimum. Okay, 0.3 is not even close to the minimum. We can even go to 0.2%. But typically, when dealing with slabs, you usually go for the rho for values below 0.5%. So why do we need the rho here? This is actually important in order to find the basic ratio. Okay, this one we can get it from a graph. This is the graph where you get the rho, the basic ratio. Okay, what you can see here in the x-axis is the row. For the slabs, it is always up to here. It is up to always up to 0.5%. So you can take it from there immediately, or you can just be very economical and go for something lower. So I'm taking 0.4%. If I go up to the grade that I'm using, which is 30, the grade of concrete, I'll end up having something like this, 25. So that's my basic ratio. Okay, I already have the span, and now I worked out the basic ratio from the graph there. And there is something here, there's a factor called the correction factor. This one we don't have to worry about, since we are dealing with a span less than less than 7 meters. We take this as 1. Okay, this is for the solid slabs. But when you are dealing with flat slabs, which can run for pretty longer spans than the solid slabs, then this number goes up to 8.5. But for this example, we just take it as 1. So the correction factor in this example is 1. Okay, so I've got the span, I've got the basic ratio, I've got the correction factor. This is what I get. This is my effective depth, D. Okay, and well, you can just view it in this way. Well, this is the effective depth. As you know, it is from the very top, the extreme top of the slab, up to the mid of the main rebar. And I'm assuming that it'll be having a rebar or a main rebar of 10 millimeter diameter. Well, we can choose between this range, between 8 to 12. That's usually what you pick up for the slab reinforcement. So I'm assuming that it'll be having 10 millimeter diameter, and for this I need this distance, the rest here. So it is 160 plus 5, 10 divided by 2, so it is plus 5 here. And then usually you have this kind of exposure cover. So I'm gonna take the XC1, which is the minimum, and this is the clear cover. It is 25, so it is from here up to here. So I'm gonna take this as 25, that's the minimum. That's the nominal cover for the reinforcement. And then I just put these numbers there. So 160 plus 5 plus 25 gives you 190. This is the overall depth. Okay, so we just move on and work on the loads. So we need to estimate the loads. First of all, you work with the self weight, which is always the simplest. And here we have the overall depth, which is 0.19 times the density of the concrete, which is always 25. You'll get this value here. And then the floor finishes, it is giving as the dead load in this example, which is 1 kilonewton per meter square. You take the total, you have this number here, that's the dead load. You go for the live load, it is only 3.5, that is the live load. Now, obviously, you need to work on and figure out the ultimate design load. In this case, as you can see, we have this factor, partial factor of safety. That's 1.35 for the dead load and 1.5 for the live load. You get this number. This is the ultimate design load. So since we need to work on the bending moment and shear force, and obviously we have it here as kilonewton per meter square, so we just simplify it and make it as per 1 meter strip. So simply just multiply this number by 1. That's the 1 meter strip, and you get this value. So eventually you end up having this figure here. Okay, this is the 1 meter strip, and this is the effective span. You have this UDL in kilonewton per meter. Now we can very easily work out the shear force and the bending moment. So the shear force, simply, since we have a symmetrical loading on the member, so definitely the R, either this one or that one here, is equal to 13, which is the load, times 4, which is the span, divided by 2. So for this one, we have a positive shear force, and here we have a negative shear force, but that doesn't really matter because we don't care much about the sign. And for the bending moment, since we have a simply supported member, then it is always this number here. So it is the load, which is 13, the WU times span or L squared by 8. This is for the simply supported members. So just 13 times 4 squared over 8 will give you this number here. This is our bending moment. This is the ultimate bending moment. So we have the ultimate bending moment, we have the ultimate shear force. We simply need to work out the shear reinforcement for this section. So as for the slab, or sorry, as for the beams, we use exactly the same formula for the reinforcement. Now we have to work out, this is the only unknown figure here in this equation. And in order to find the lever arm, you have to use this formula as well. That's the K, and it is something here related to this graph. And the K, you can work it out from this formula. K is equal to mu divided by BD squared, the grade of concrete. So that's 26 times. So that's the bending moment here. And then we divide it by this fixed number. It is always 1000 for the slab. And then we have the D, 160 squared times 30. You get this value. Now see, if you have a value less than 0.05, you always take the maximum Z, which is limited to 0.95D, okay? Or you can just take it from this graph. This is a 0.05, and if you go up to this point, you can't go farther. This is the limit, so you just go always for this number. So I mean, if you take a number there, or I don't know, maybe here, you can't go farther, you can't go for 1, you always take the limit here. And remember, for the slab, we don't have, usually most of the time, you don't really have the compression reinforcement. You can't get the K equal to or more than 0.167. Okay, remember the K is very small for the slabs. It is always, almost all the time, very low. So we take the Z as 0.95. Okay, let's just plug in the numbers there. We have the bending moment, the maximum bending moment, we have this factor here, and the yield strength of steel, and this is the Z, we get this value. This is the area of steel that we need to use for this slab, for this particular slab. So if you have this table, I mean, this is the table that you use for the slab. It is different from the beams. It gives you the spacing of bars and the bar size in millimeters. So go and pick up a number a bit larger than this. So for this case, I'm gonna go for H8 at 125 millimeters center to center. So that's 8, and then so here you have it. That's the H8 125. Remember, this is the AS provided, but this is the required. Okay, we will need these, the required and the provided later on for the deflection verification. So we provide this one here as the main reinforcement. Now, just to verify that the deflection is fine and we don't have to worry about any kind of excessive deflection, you're gonna need to go back for the row and then use this required area of reinforcement. Okay, this is the required, just put it there. You get this percentage for the row, that's the percentage of steel reinforcement, and this should be larger than the minimum required. That's the first thing. And the second thing is, again, go back to the figure, just try to find the basic ratio again. If you get it something like this, up to, I mean here, the number corresponding to this percentage. So in my case, it's 36. This is the 36, and the actual span to effective ratio for our case, we have the span for 1000, we have the effective depth as 160, we get something like 25. So 25 is less than 36. Hence, deflection requirements are likely to be satisfied. Okay, that's one way to check the deflection. That is not going to be, the deflection is not going to cause any kind of troubles later on. So we're done with the deflection. So we move on to the secondary or transverse, or even called distribution reinforcement. Okay, these are the distribution reinforcement. So we provide the minimum reinforcement, which is 0.13% BD, okay, to control thermal and shrinkage cracks. They only there to control the shrinkage and thermal cracks after the concrete support. Okay, so we provide the minimum AS, which is 0.13% BD. So 0.13%, this is the 0.13% times B times D gives us this number. Go back to that table, provide this area of reinforcement. And this is the table, and we're providing something larger than this. So 223. So it is this one here. Again, remember, you just go for the same diameter. You don't really have to go for the lower or bigger diameters. Just take the same one. So we provide this area of reinforcement for the secondary reinforcement. Okay. All right, let's just check the shear capacity. Remember, when you are designing a slab, then the shear isn't really that big deal. Usually the slab has enough capacity to resist any kind of shear stresses. That's without considering any kind of shear reinforcement. So we have the shear capacity, which we worked on very early, and it is just at the center of the support, but we don't need this shear force. The one we need is this one here at the face of the support. And just draw the shear force diagram, and then that's what you need at a certain distance here. You have this triangle here, the small one, and you have the bigger triangle, this one there. So we have this distance, we have this distance, this is the long distance over the short distance, or you can just take it the short distance over the long distance. Okay, and we have the maximum shear force by the one that we have to find out, which is VED. Okay, so VED, the small one, over the maximum, or over the big one. And then we have the small one, this distance. You can work it out very easily. So it is 2 meters minus the thickness, half of the thickness. So it is minus 0.5 times 0.25. It will give you this figure. So this one is this distance in red. So the small distance over the large distance, and then you simply can't find the VED. Let's just check it if it's within the capacity or not. So this table gives the shear resistance for the slabs without shear reinforcement. This is only for class C30, 35. But there is this table here. There is a factor that you have to multiply by. If the rho is less than 0.5, then no modification is applied. Okay, but in our case, we are doing this example with the class of C30. No need to consider this modification factor. Okay, so C30, where is the C30? The slab, the effective depth is less than 200. This is the shear resistance of that cross section, and it is equal to the shear stress times PD. Okay, so the rho for our case is exactly 0.25%. Okay, this is the area provided. Don't get yourself confused with the AS required. This is the provided. So it is exactly 0.25%, which is this one here exactly. So it is less than, definitely our G is 190, H is less than 200. Simply take the stress, which is 0.54, times B times D. It will give you this value in Newton, and then just divide it by 1000, you get this value. this is way less than the shear resistance of that cross section. No shear reinforcement is required. That's it. Okay, there is the simplified curtailment rule for simply supported slabs. And that basically means along this distance, okay, 0.8 L, we provide the maximum, or sorry, the whole reinforcement, the 100% of reinforcement up to this area, up to this length only, 0.8 L. But for 0.1 L near to the support here, for the simply supported slab, we only provide steel of 50%. Okay, so simply provide here the entire reinforcement that we calculated, and here when you are approaching the end or approaching the support, then just provide 50% of the reinforcement. This is just to save money. That is the main idea of curtailment, to save money. Okay, so we make it in this way. We provide the entire reinforcement of the 100% reinforcement here, and then we just reduce it here to 50%. Okay, we have the 100% reinforcement here. This is the 100% reinforcement here. But when you enter this region, you just provide the 50%, and the 50% of this one here gives the H8 at 25 millimeter center to center. So it is just half of this number. Okay, if you check it from that table, you get this number. Okay, or you get this reinforcement. Remember, you use the same diameter. You don't go for any different diameter. Obviously, you just make the spacing a bit bigger there. So that makes it. That's all. We have the distribution reinforcement, and we have the main reinforcement, but here we just reduce it for money saving from that side and this side as well. Thank you for watching, and hope you enjoyed it. I'll see you in another video, and hopefully we're gonna discuss something related to a continuous one-way solid slab. Till then, thank you very much for watching. See you later.